Hi, welcome to the Calculus 3 lecture series. We are in the unit about partial derivatives. And this is our last topic in this unit. And this topic is we're going to talk about is a Lagrange multiplier. And so before we start, let's take a look at what is the Lagrange multiplier and what it tries to do here. Okay, so let me go to our worksheets here. Okay, so let's go ahead and take a look at what is the Lagrange multipliers mean and what type of the problems we try to do. Okay, so let's see if you still recall in the Calculus 1, right? So in the Calculus 1, we call this optimization. We have the optimization problems. So what is the optimization problem? So for examples here, right? One of the typical problems we kind of doing in the calculus, like we did in the Calculus 1, very popular. It's like a farmer have a certain material of the fence, and then they want to get the biggest areas here, all right? Okay, so now let's take a look here. So that's why we said, okay, so typical we say, okay, I have the certain, I want to have like the rectangular farmland, right? So I have the material. So for example, the fence material, I have like 200 feet of the fence material, and then the farmer want to get the maximum area, right? So how do we do that? So what is the dimension for this rectangular farmland here? So like in the Calculus 1, so what we did here? So we said we have one of the first things here. So we have objective functions, right? So this objective function is the sense that we want to maximize or minimize, right? So for this problem here, we say, okay, our objective function is x times y here. And then what do we want to do here? We want to maximize the x times y here, right? So we want to maximize that. And then we also have a constraints. So for these constraints here, we say, hey, the total fence material is 200 feet here, right? So how do I under these constraints, so I know the perimeters is 2x plus 2y. That is what is 200. That means this is the constraints I need to follow. So we got the x plus y equal to hundreds here. So in the Calculus 1, what we did, then the next things here, we say, let's do a substitution. Okay, so let's do a substitution. So we say, hey, I can change the y equal to the 100 minus x, right? Then I substitute the y back to my objective function. So my objective functions here will be the x, then this is 100 minus x here. So this turns to be a function of the g. So I have a function x minus x squared. So I want to maximize this. Then what we did in the Calculus 1, we say, hey, let's try to find a critical point. So I find the first derivatives, right? So you set the first derivative, then you set the first derivative equal to 0. And then you find the second derivative. The second derivative is here is -2. Because it's -2, so I know the function open downward, right? So concave down here. So that's why I know I have maximum values here. That's what we did in the Calculus 1 here. Okay, so now in here, what is a Lagrange multiplier? Is we try to do these optimization problems in R3, R4 situations here. And, one of the problems here, in the Calculus 1, so these constraints here, right? So you'll be able to find the variable y, you'll be able to replace one variable with other variables here, right? But now in here, how about the constraints is kind of complicated. You cannot do that. Then what we need to do is here, Okay, so that's what is the Lagrange methods here. The Lagrange method is kind of like the intuitively, you know, if you give me a function z is equal to the f of x y's here, right? So for the z is the f of x y. So you know, if you take a look at the surface curve. Like for this function, maybe it will be something like this, right? So this is what we call the surface curve. So like then you give me some constraints here. So my constraints could be like, you know, the different things here. So now the constraints, so basically you look here. So you know, it's kind of like, for example, if this is your constraints here. Okay, so I typically like to use the example as, you know, you want to climb in the mountains, right? So this is what we call is the contour map. You want to climb in the mountain. Of course, you want to get it as high as possible, right? But if this red ones here, if this is the park that tell you, hey, this is my trail, you have to do here. So then you know your highest point you can reach really is the trail, and you know, kind of touch your contour plot, right? So like in here, you know, this is the highest point you can reach here. So from the previous partial derivative, so we learned two things. We say, hey, you know, if this is my level curve, then my highest my highest you know, the direction will be what? My highest direction will be the what? The gradient vectors, right? So this is the biggest rate of the change is over this rate, these vectors here. So now here, this is my, you know, my constraints. So the same way is here, right? So like here, if they touch here, then I also know from the constraints. So here, if my constraints is gxy here, then the biggest rate, you know, the biggest rate of change will be on the gradient vector. So if this is like gxy, so I know then the gradient vector for the constraints here will be in the same directions, right? So in the same direction, so they will be different by a constant of the, you know, the gradient vector for the level curve to your original function. That's the whole ideas about the Lagrange multiplier. Okay, so now if you take a look, this is our definitions, right? So they said if, okay, so it said if x, y, and gy have the continuous partial derivative, and the AB is a local extrema for f, and then what is the constraints here? The constraints is here, right? It's constraints by the gxy equal to k. And then we say, okay, then there is a constant here. That means the gradient vector for both those functions, they have to what? They have to kind of go into the same direction and will be perpendicular to their what? Will be perpendicular to their level curves, right? So now we solve this lambda, and the lambda is what we call is the Lagrange multiplier. So it can solve the problem just like you know, in case you cannot do the substitution for one variable to the other, or when you go to the higher dimension, it's become more complicated, right? Okay, so now let's take a look here. So the number one is here, right? So I want to find the extrema of f of x, the x squared minus 4x plus 2y. So okay, so I know so let's start here. So del y, so this is the gradient vector. So this will be what is the 2x minus 4y. And then I have negative 4x plus 4y's, right? So this is the gradient vector. And for the function f of x, which one I want to find the maxima or minima, then the del g is here, right? The del g is a derivative of this constraints here. So it will be gx will be 2 and negative 3. So based on the the Lagrange multiplier, so I know that del F is equal to lambda del G is here. So I can say here, then the first thing is here, I have 2x minus 4y equal to 2 lambda. And the second one is here, I can have negative 4x plus 4y equal to the negative 3 lambdas, right? So if you take a look here, so you see here we have x, y, and the lambda. We have 3 variables, so we need to have 3 equations to solve it. So what is the other one? Hi is my constraints, right? So the equation number 3 is here. This will be the 2x minus 3y equal to what? Equal to 14. So like for the Lagrange multiplier, try to find the optimization for the max or mean. The concept is pretty simple. The hardest part is the algebra part, is how do I solve the system of equations here. Okay, so now let's take a look here. So first of all, I want to solve it. So I will say here, I can do equation 1 plus equation 2. Equation 1 plus equation 2, y cancel, you will have a negative 2x equal to negative lambda. Right? So then you can find the x equal to the lambda over 2 here. Okay, so now let's try to cancel the x here. So I will say equation 1 times 2 add to the equation 2. Let's see what we have. Equation 1 times 2 is positive. So it's negative 8 plus positive 8, negative ay plus positive 4y. So I have a negative 4y. The times 2, this is 4 lambda plus negative 3 lambda is 1 lambda here. So y is equal to the negative lambda over 4, right? Then I have in here, right? So I have x here. This one is not too bad. Then I can both substitute to my third equation, so I can solve it. Okay, so now in here, I will have the 2x, right? So 2, the x is 1/2 lambda plus minus 3y. Y is what? Negative lambda over 4 is equal to what? Is 14, right? So now you will have lambda plus 3/4 lambda equal to how many? Equal to 14. So now here is 4/7 lambda equal to 14. So I guess the lambdas here will be 8. Okay, so the lambda I find here is 8 here. That's good here, right? So if the lambda is 8, then I can say here, so x here, so x equal to the lambda over 2, so this is 4. Then y is equal to the negative lambda over 4, so it's negative 2. So I know I'm going to have the 4 and the negative 2. At this point, I will either have the maxima or minima. So I substitute the f of the 4, negative 2, back to my functions, right? Back to my function, f of x functions here, xy function, I will get a 56 here, okay? So now we need to see, is the 56 is max number or is the minimum numbers here, okay? So let's take a look here. So we said here, okay, so in here, okay, so let's see here. So we know, so here, so we know if the 2x minus 3y equal to 14, so I know the y is equal to what? 2/3 of x minus 14 over 3, right? So as you can see, so x here. So if x is large, then the y going to be large also. Okay, so and then the y going to be large. So if x is positive, if the large value of the xy, so if x is positive, right? So if x is positive and the y is positive, then when you plug the number, so back to here, you will find the f of xy here is give you the negative number. So which one is less than 56? So if x is, if x is a large negative, if x is large negative, y is large negative also, right? Y is large negative also. So that means the f of xy also going to be what? Also going to have the negative number. Okay, so that's why I know the 56, right? 4 to the negative 2, this is 56. What is this ones here? This will be the maximum numbers here, right? So I know for this one, I have the maximum number. I did the contour plot. So let's take a look at the next page. So from this problem, you probably will get a better idea. Okay, so like the graph here. So this graph here, right? So this graph, this is the graph of xy in the 3 dimensions. So you can see here, right? So this is really, it's kind of like saddle, like the horse saddle, right? So it's kind of like these ones go up, this side going down here, right? Okay, so now this is the cross, this is like a contour plot or the level surface. So if you do level surfaces here, okay, so now in here, right? So the red ones here, the red lines here, this is the line, this is my constraint, 2x plus 3, 2x minus 3y equal to the 14. So the 2x minus 3y equal to 14, right? And then you can see here, right? So this is the red one, they touched all the level curves here. So this blue dot, that's the one, this line tangent touched the level curves here. So these ones here at the point 4, 2, 4, negative 2. You see here, so this is 4. Okay, let me see here. So this is a 4, and then this is a negative 2, right? So it's a 4 and a negative 2 here. So, like in here, right? So this one's here, right? So from here, this one, it will be, right? So of course, for the true value of f of xy, so this f of xy is bigger than the what of 56, but that doesn't matter. I'm only look at the value on these lines here because that is my constraint. So if you take a look at these lines here, you can see this line tangent this level curve. So this line going to touch the others level curve here, like here. But because my level curve is like this, if I get larger here, right? So like here, so all the others, the level curve line, this restriction line, constraints line touched is smaller. So that's why this is the max values here, okay? So that's why, if you do a graph and it will be easier to visual, just like you say, of course here you can get f of xy values a lot bigger, like here we can go to infinity, but it doesn't matter because I'm only looking for the value of this line touch. So like I said, this line will touch the several other level curve, but it doesn't matter, it's smaller, right? So the only ones here, that's why this number is the max numbers here. Okay, now let's take a look at the next ones here. The next ones here, let's say find the system of equation. I want to maximize f of x, y, z And then now I have two. Okay, so here I have two constraints. I have this one and I have this one. This is also one of the things we cannot use the substitution method in the calculus 1. We know how to do it, right? So we cannot do that. Okay, so now we use the Lagrange, so the same way. So let's do the gradient. So the gradient vector will be 2x plus 6y, right? 6y squared plus 3z squared, and the y, delta fxy, so it will be 12xy plus z3. Then the last one is f of z, so this is 6xz plus 3y z squared, okay? So now after this one's here, then you say, okay, so this is the, I can call this is gx, then this constraint I can call is h of x here, okay? Or you can say g1, g2. Okay, so the del g is what? Del g is 1 and 1 and 2z, right? That's del z. And then del h here, this will be what? This will be 2x11, okay? Because right now I have two constraints, so I need to have two Lagrange multiplier. So I know the del f is going to be equal to the lambda 1 del g plus lambda 2 del h here. See here, you have two Lagrange multiplier. Okay, so now let's just write it out. So this one is 2x plus 6y squared plus 3z squared, 12xy plus z3, 6xz plus 3yz squared, then plus lambda 1, G is 112Z. Okay, it's 1 like 2Z, and then plus lambda 2's here, it will be what? 2x11. Okay, so when you multiply that out, you will find here, you will have your first equations here, which will be the 2x plus 6y squared plus 3z squared is equal to lambda 1 plus 2x lambda 2. Then the second one here you will find is 12xy plus z cubed. It will be equal to lambda 1 plus lambda 2. Then the 3 here is going to be 6xz plus 3yz squared is going to be equal to the 2z lambda 1 plus lambda 2 here. So now let's count how many variables we have. We have lambda 1, lambda 2 is 1, 2, right? And then we have x, y, z. So we have 5 variables. So far, I only have 3 equations. So where is the remaining 2? Are those constraints, right? So the equation number 4 here is x plus y plus z squared equal to 2. And the equation number 5 here is x squared plus y plus z equal to 3. Okay, so now this is what we call this the system of the equations we want to solve. Right? You have 5 variables with 5 equations. Ideally, we should be able to solve it. All right. Okay, so but in this problem, they just said, hey, try to find the system of equations here.